Good afternoon. Thank you for coming out on a fine Sunday afternoon to hear my presentation on protection mechanisms and how you can apply them to IP networks and how you can apply them to IP technologies. But before I get into that presentation, I just want to make mention, if you have not seen this posted around the meeting space or saw it at the registration desk, Cogent is sponsoring a networking reception tonight from 7:30 to 9:30. So if you're interested in more information, go to the registration desk and you can get more, or you can go to the NANOG homepage and follow into the NANOG 20 stuff and get details. My name is John Sadler. I'm with Tellabs. It's actually only been a couple months that I've been with Tellabs. Before that, I worked for an Arbach in their long-distance area, and before that, I worked for a company that did network protocols. And today, I'm going to present to you a discussion of protection mechanisms, how they apply to some of the technologies that you experience today when building networks, as well as how they can apply to IP technologies in the near future, and therefore allow for increased IP network survivability. Motivation behind this discussion comes primarily from the new applications which are going across the internet, and those applications are requiring they're requiring a very stable network infrastructure. They're mission-critical traffic. They cannot take time hits. A good example is a friend of mine works for a company that does derivatives trading, and in their environment, a half-second hit loses them billions of dollars because of the fact that they're playing the stock prices across the different markets across the world. And so they have resisted moving to things like ATM networks and even public IP networks because of the fact that their business is so dependent on the reliability of the network infrastructure that's underlying their communication systems. Anytime you have high priority critical traffic, you need to have a network which is capable of responding very fast to these faults. And protection is one of the ways that exists today to do that. Now, protection schemes exist at multiple layers in the communications stack. They aren't something that apply specifically to SONET, which is the place that you probably heard about them before. Protection is an automatic mechanism for recovering a traffic path. Keyword there is traffic. It's not transport that's being recovered, but traffic that's being recovered. It's invoked when a working path fails. The key requirements are the fast restoration time. Protection mechanisms are typically designed to deal with 50 millisecond or less hits on the actual traffic that's being carried. They need to be predictable. You can't have issues due to scaling that suddenly cause these numbers to increase. Typically, in order to meet these requirements, protection paths are predetermined. They're not something that are dynamically determined on the fly as network changes occur, but rather at the time that a service is set up, the protection path is established, and then when there's a failure in the network, it is utilized. These protection paths can be dedicated. You can have a protection path allocated at service setup time specifically for that service, or it can be used for a group of services that you may be protecting. For example, let's say I have 3 cable routes across the U.S. Does it make sense for me to have a service that's going across the north route and a service that's going across the middle route, both individually protected at the south route? The answer is probably no. Instead, you probably can have just one protection path running on the south route, which you can share by your north and mid services. But this does lead to an issue of how do you deal with double faults. And so you have to have some sort of preemption mechanism in place so that you can determine whether or not what's currently on the protection path should stay there or should be removed. So protection can also be preemptive. Now, why would people want to use protection as opposed to dynamic rerouting? Well, dynamic rerouting develops a new path based on current network state information. So if you have a failure in the network, you have the need for the failure information to be propagated for all of the devices in the network to then process that appropriately, and then services can be restored. The delays associated with identifying a failure and also the flooding of the updates causes dynamic rerouting to take more time than protection. Now, I know there is another presentation later in the NANOG conference talking about how to reduce those delays. I'm certainly going to be very interested in what they have to present. But the result is that protection mechanisms, because they're pre-developed or predetermined, can typically restore a lot faster than dynamic rerouting. There is also one side effect that comes from all of the state information that's flooding through the network. Let's say I have a network that has a number of nodes which are involved in a service path, and then one of the links connecting those nodes together fails. Well, all of the nodes within that area or within that larger network will find out about that link failure and will then go ahead and process for it. And it could be that they have no services that were really impacted by the link failure. So the result is that you do have some systems in your network which end up taking a lot of additional CPU time to handle rerouting for some event that really doesn't affect any of the services on it. Protection is typically localized to the nodes that are involved in the actual service paths, both the working path and the protect path. Now, best effort services certainly can tolerate the behavior of dynamic rerouting. You know, after all, if a web page takes a couple retries in order to get it, people typically will accept that. But new services like voice over IP or virtual lease line, where you have companies replacing their lease line infrastructure with underlying VPN services, can't if they have mission-critical data running over it. An important part of dealing with protection mechanisms is discussion of the protection domains. It doesn't make sense for you to have the world as one protection domain. Instead, it makes sense for you to break up little chunks of the network and have them work amongst themselves in order to protect the traffic that's going through them, and then to have those domains coordinated amongst each other. You're probably saying, well, gee, this sounds a lot like OSPF areas or ISIS areas. In reality, it's the same, break the elephant up into bite-sized pieces problem. But the big difference here is the fact that protection domains are typically small. A lot of people will set up protection domains with only 15 or so nodes in them. They will not set up networks of 200, 300 nodes and then try and implement protection across it, because you start getting into some scaling issues related to propagation of information. So the main protection topologies that you find people implementing in these small environments are linear, ring, and mesh. And I'll define some common terms here for all three of those. Working circuits and protect circuits. A working circuit is the path or span that's being used to carry live traffic. A protect circuit is the path or span being used to recover that live traffic. It may not necessarily be a dedicated path, but nonetheless, it's a predetermined path. I'm going to step through these different topologies so that you can understand exactly some of the other terminologies associated with them. What I have up here right now is linear protection topology. And you see here a number of devices, or two devices connected to each other across a span. And the first, the one on the left, collection of nodes is in what we call a 1+1 arrangement. Here we have a dedicated protect span for every working span. So you see two working spans and two protect spans, hence so 1+1. In the second pair of nodes, you see three working spans and two protect spans. Once again, this could be characterized by, or it could be an example of the network I described earlier, where you have three different paths across the U.S. You may not need to have a protection span for every working span. This is known as shared protection, or M-to-N, or 1-to-N protection. And the big difference between dedicated protection and shared protection really comes to the actual mechanisms. We'll talk about mechanisms next, but with dedicated protection, you can typically get faster protection switching than you can with shared protection. Everybody here, I assume, has heard of SONET rings. Well, ring topologies are very easy to protect because you have an easy to define secondary path to take traffic around the ring. There are a couple of special names, though, that exist in SONET rings that you may not have heard of. Here we have a ring of 4 nodes, and you see the black lines connecting those nodes together. Those are the actual fibers. And then you see the red and blue lines. That's the actual services that are being carried across this ring. So you see a service that's coming into the ring in the upper left and going out in the lower right. And by the way, this is a bidirectional service, so there's a converse path too. For this ring, the nodes have what are called line interfaces and drop interfaces. The drop interface is the actual service delivery interface. This may be going to a customer or maybe going to another protection domain. The line interface is the part which actually connects all of the nodes in the ring together. It is not something that's customer-facing typically. There are 2 line interfaces in a ring node, and in order to better describe which interface you're dealing with, the east versus west interface naming has come up. So one side gets named east, one gets named west. The drop interface can be called the southbound interface, and I guess nobody's using northbound today. But the reason why east and west exists doesn't mean that the node has to be oriented so that one interface is pointing one direction and the other way. It's rather to talk about the fact that you have interconnection of these 2 nodes, and you don't want to have 2 east interfaces or 2 west interfaces connected to each other. It should be east to west all the way around the ring. In a mesh topology, this could be a sparse mesh. This doesn't have to be a complete mesh like I've shown here. And in this environment, you have 3 or more nodes that are connected to each other, but there isn't necessarily a well-defined path for the protection to take. Instead, you have to be able to compute the actual path that would be used for protection or provision it. Some human person would have to determine it. These spans can be individually protected, the actual connections between the nodes, so like right here, with linear protection. So it's actually possible to further subdivide this particular protection domain into a sub-protection domain with linear spans, linear protected spans. But the overall connectivity of the service in a mesh network is still protected because of the fact that you have these multiple paths to take through the network. This probably reminds you a lot of IP networks. Most IP networks are best characterized as a mesh. Here you see, hello. Well, I guess free is worth something, right? Here we go. Okay. Here you see the working path on this particular mesh. Here you see the protect path for the service. Between these 2 interfaces within the mesh, you therefore have the recovery capability. Now, protection mechanisms are the actual algorithms that are used to do the actual service restoration for a particular network topology. They usually take advantage of topology characteristics. For example, in a linear connection that you're protecting, it's really quite simple to know where the protection traffic is going to go. It's going to go on the other fiber, right? Whereas in a mesh network, you have full path development that you have to go through. Now, there are 2 different types of protection mechanisms that exist. There are link-oriented mechanisms and there are path-oriented mechanisms. The big difference between the 2 is where are the decisions being made and where are all the configuration changes being made in order to actually affect the protection switch. In a link-oriented algorithm, you have multiple links that are being changed at all the nodes in the path going from source to destination, and those changes are being made in order to switch the traffic over to the protection path. In path-oriented network restoration, you typically have two paths that have been pre-established, and then you have a global switching which occurs, where devices at the ends of the paths make the decision that the switch should be made, and then it happens within the network. So the individual nodes that are intermediate between source and destination aren't necessarily involved in the actual protection switch. First example of this is linear APS. This is an example of a linear 1+1 protection mechanism. You have two nodes connected to each other with two or more sets of transmission facilities. When there's a failure, there comes the backhoe. It's the responsibility of one of the two nodes to identify the failure of the facility. Now, typically that's the receiving node on the particular fiber or whatever that's been failed. You can actually have a bidirectional facility where only one side fails and the other side stays up. That node will then signal for a switchover to occur, at which point both nodes communicate with each other and the traffic is switched over to the protection facility. That communication is typically done out of band, not actually in the payload path of the traffic being protected. It could be that it's in some quasi out of band thing, like in SONET it's actually done in the overhead bytes, not actually in the STS payloads. Or it could be fully out of band, example being something like the SS7 network. Another protection mechanism that exists in the ring environment. This is called bidirectional line switched rings. And if we break down the name, we can understand exactly how it acts. First off, it's bidirectional, meaning that when you have a protection switch occur, both directions of traffic are going to be switched to the protect path at the same time. Now, this means that if you have a failure, say, of only the receive path, you still can have where your transmit path will also be moved. So you'll see hit in both directions. Line switched means that the individual nodes between where the traffic is coming into the protection domain and where it's leaving the domain are all going to do some sort of reconfiguration in order to bring the service back into working order. What happens when there is an actual failure, this time we have a faster backhoe, the node that determines there's a need for the signal to change will signal out of band to the other node. As you see here, the switchover message going from the egress node here back to the ingress node here. And all the intermediate nodes will then reconfigure to use the new path. And you can see the actual changing of the colors of the service paths in order to bring the service back into working order. Now, BLSR, in comparison to other ring protection mechanisms, is actually quite efficient. We'll get into a discussion on that in the next slide. However, because of the fact that you have all this signaling going on, it's not necessarily as fast as some of the other protection mechanisms. Here you have an actual message that has to go from one of the nodes back through all the individual nodes to the source node, the switchover, and then the acknowledgments coming back, causing the individual intermediate nodes to also switch. Why is this more efficient? Well, because each node is aware of the use of the path that's going from ingress to egress in the protection domain, they can determine whether or not other traffic could be put into the protection line. If you can declare one of your paths as working and one of your paths as protect, that protect path is not in use. It's sitting there idle. And so what will happen is a service provider will say, gee, I can make money using this protect path, but of course I have to let my customer know that it's not going to have the same availability as if it had been a protected or even an unprotected service. This is called extra traffic. I don't know if any of you have been approached by your carriers on use of extra traffic. It can be a cost-effective way to getting connectivity But the key thing to note is that if they have a protected service that needs to use the protection path that your service is in, you will get bumped. This is that whole preemption thing that I talked about early on. Why does it take more time? As I mentioned, you have a signaling latency. Plus, if you are using extra traffic, if the service provider is using the ring for extra traffic, then they have to change the cross connects within the individual ring nodes in order to remove the extra traffic from the ring path and put the protected traffic back into working order. These cross connects don't happen instantaneously. Another type of ring protection mechanism is UPSR. Again, let's decompose the name. Unidirectional, meaning that each direction of service for a particular service is protected independent of the other direction. So receive could move over to the protection path, but transmit could stay on the working path. Path switched. This means that the end devices to the communications path are the places that the decisions made and also the changes made. No individual changes are necessary in the whole ring or protection domain itself. It's just at the endpoints. And once again, ring, because it's a ring topology. In this environment, you have the source node. In this case, let's talk about the traffic that's going from A to Z, creating two copies of the data and sending it on the two paths that have been established. The destination node, which is taking the traffic off of the ring, then will look at both copies of data and choose which path is best. It could be that one path has bit errors on it. It could be one path has actually been broken by a backhoe. But it's the destination that makes the decision. The result is that you end up with a very, very slow switch time because there's no communication that's necessary amongst all the ring nodes to make the change. See, no communication necessary. It happens automatically. The problem is it's not efficient. You have both sides of your protection domain carrying the traffic so that you don't have to have all this signaling. In some cases this may be worth it, in some cases it may not. Mesh environments are a little bit trickier than both linear and ring environments. Typically they're set up with end-to-end path communications. So the destination node in the path has to determine if there's been a failure and then signal to the network that a switchover is going to occur. But the first thing, which is most important, is how do you determine what those paths are through the network? This requires you to have a mechanism to do topology discovery, determine what the actual network graph looks like, to do constrained route selection. Last thing you would want is for both paths to go on a common fiber or a common underlying transport facility. So the constrained route selection allows you to say, I want one route, I want to know the particular devices that are involved with it, the particular cable paths, the particular conduits, all the way down into that conduit structure. And then I want a second route which totally avoids everything. So what you've just done is created a constraint. And then last, you need to have a signaling protocol to, number one, set up the paths to reserve the protection path, even though it may not be used, because it may not be used immediately, as well as also to do the notification that a failure has occurred and that a protection switch should go on. The problem is that nobody's come up with a standardized way of doing mesh protection yet. If any of you are thinking about, well, gee, in IP we have mechanisms to do rediscovery and route selection and a way to signal when there's a change, you've got a clue as to what may be coming. Later in the slide decks, I'll talk about that. Now, these mechanisms all have one common issue, operational issue, that you need to keep aware of. And that's, when do you actually switch back to the path that has failed? Do you do it immediately? Do you wait for a period of time? Do you require a human being to say, revert? There are some people who say, well, let's have it automatic, which could be good, except for if you don't have a hold time as for when, after service has been restored, you switch the traffic back on to the transport path. You could end up with a thrashing condition. Let's say you have a problem with a piece of equipment that can't deal with certain one's density or zero's density in it. Maybe it loses synchronization. Well, if the idle signal that you're sending is automatically causing inversions to occur, and therefore the synchronization isn't lost, you can actually have a service that looks like it's been restored, the transport facility, that's been restored, yet when you actually put traffic on it, if it doesn't meet the ones or zeros density issue that the piece of equipment is having, suffering from, then you could actually end up with failures again on that path. So you don't necessarily want to have automatic reversion without a hold time. Another good reason why you want to have a hold time is, let's say it was brought back into play because one of your technicians happens to move a fiber around and it comes back up. And then they happen to move another fiber around and it goes back down. And then they move another one around and it comes back up. The technician's thinking, I'm trying to figure out what the root cause of this issue is, why the service is going up and down, or the transport's going up and down. But in reality, you're taking multiple hits on your services that are being routed across that particular piece of transport. So having a hold timer, even if you are using active reversion or automatic reversion, is definitely a good idea. Manual reversion can be good to deal with some of these issues if you don't have a hold timer capability within your equipment. However, you can also end up with people saying, well, I'll take care of that Monday when I come into work. And guess what? Someone may have updated a database saying, oh yeah, it got moved back onto the working path, but in reality it's still on the protect path, and all of a sudden during the weekend there's another failure which occurs somewhere else in the network, and that protect path is available, right? No. And so you end up taking both services down, the one that you had restored on Friday and the one which failed during the weekend. So manual reversion can be good if you have a good lockstep between your inventory systems and the equipment. But if there's any possibility for those two getting out of sync with each other, you probably want to have some sort of automatic with hold timer in use. Now there are times when you do not want to have traffic revert back to the working path. A good example of this is when you're doing a service role. Let's say you just finished build out of a brand new fiber facility, or just turned up some new T1s, and you want to move services over to those new facilities because it's a more direct path to the customer, or maybe it's a lower cost facility for you to use, whatever. Well, protection mechanisms provide you a nice rolling facility. You can connect up your new facility as the protect path for the service that you want to roll, and then fail the service you want to roll, and whammo, it's now on the protect facility, and you've achieved that in very, very little time, faster than any human can provision a piece of equipment. So the result is that you get a good service roll mechanism. Now, the last thing you want is for that equipment to think, well, gee, I just saw carrier come back up on this other facility and revert back to it because most likely you've changed the configuration of it, and the service would end up, that had been rolled would end up being affected. Now, when you have multiple domains going on across your network, it is possible for you to have protection occurring within each domain individually, as well as for protection to occur across all your domains. And sometimes you want it to be global repair, and sometimes you want it to be local repair. The issues here have to deal with the entropy that you introduce through the local repair issue. If you have local repair going on, you could end up with less efficient resource utilization across your whole network for the period of time that you're switched to the protection path. So the result is that most people want to institute global repair at a service level, and local repair at an underlying transport level. We'll get into protection hierarchies in just a moment, and you understand a little bit more about this. Hey, look, protection hierarchies. Now, protection functionality does exist for all the protocols I have up here. At the optical layer, there are a number of proprietary solutions. At the SONET layer, there are a number of standard solutions. ATM and frame relay have the IE630 standard defining how to do protection. MPLS IP actually is a work in progress within the IETF on how you would actually do protection with MPLS. And I'll talk a little bit about that in a moment. Now the thing is, you could end up with all of these protocols in use as you're delivering an IP service. Do you really want to have protection active at all the layers at the same time? Well, there's one camp that says, gee, protection is good because it allows us to restore services in fast times. What does it matter if there's another layer which is trying to protect? There's another camp which says network facilities are expensive, and having protection where you may end up with a lot of bandwidth being allocated at each layer in order to protect one service is not necessarily a good idea. Furthermore, you can end up with some thrashing issues. Let's say you have automatic reversion going on and you don't have a hold timer. You could end up with protection occurring at the optical layer and because of a failure, but at the time that it reverts back, what happens to all the upper layers? The reversion typically isn't hitless. There's typically a failure that gets noticed by the next layer up in the stack. So do you want all those other guys reacting? You know, SONET will react, that's not hitless, so ATM will react, that's not hitless, so IP will react. Typically, you do not want to have multiple protection layers active at the same time. However, there is a good reason to do 2 layers. Most providers are adopting a 2-layer recovery model where they use optical or SONET restoration basically as close to the dirt as you can get, because it gives them the biggest bang for the buck in terms of restoration. Let's imagine that you have a particular fiber that has on it 20,000 services. Now those could be individual routes, those could be individual T1s. Do you want to have your upper layer mechanisms trying to reestablish each service individually, or do you want to have some underlying facility which is capable of taking the whole bundle and reestablishing it at once? So using as low a possible layer as is available to you to do your first level of restoration is typically a good idea. And optical is definitely the way that the network's going. But you do need to have some sort of service level restoration too. To put it all at the optical layer means that you expect the optical devices to be able to determine bit errors, framing errors, runts, all these things that could signify a particular piece of equipment failing. Remember, the optical layer is only capable of saying, light on, power level looks good, so you can't rely solely on the optical layer to do your protection switching. You have to have something which is intelligent about the service semantics that are being delivered, acting as a last line of defense, if you will, for failures that are occurring within your network. But then you have the layers in between turned off in order to get the efficiency. Now, one issue you do run into here is, what happens if I have a service level or a service layer which is capable of restoring in the same time frame as the optical layer? Do I want both layers to do the protection switch and possibly end up with the same thrashing scenario that I mentioned earlier? Typically, what a service provider will do is they'll set their upper layer protection to have some sort of hold down timer where they'll wait for the underlying transport that they're using. It could be an optical facility that's been protected to restore before they will try and restore. So it could be that IP is set to wait 150 milliseconds to restore, and the underlying optical network tries to restore within 50 milliseconds. That will reduce this thrash. Gee, I think I've gone through all these bullet points. Basically, this is talking about why you want 2 layers. Any other issues I want to talk about here? Nope. Okay. Now talking about protection in SONET. Now this is the environment you probably are most familiar with when it comes to protection services being available to you. SONET offers linear APS, UPSR, and BLSR protection mechanisms in different network elements. BLSR is available in two different flavors, one which is 2-fiber and the other which is 4-fiber. The difference between the two has to deal with where are you going to first attempt to do restoration around your ring. In 4-fiber, you're capable of doing what's called a span switch. Think of it just like linear APS between two neighboring nodes. So if I have a ring and this node suffer a fiber cut which only affects 2 of the 4 fibers going between them, I can actually move the transmit and receive paths to those other 2 fibers and restore the ring without having to use any other bandwidth around the ring. However, how often do you end up with a fiber bundle only getting partially cut? What happens with 4-fiber BLSR that's different than 2-fiber BLSR is when the restoration is done, rehealing the ring around the other path, it's done on the other 2 fibers that exist. Those other 2 fibers then, because they're used, do not end up with you having to reserve STSs for your protection protection of your working traffic. You can instead say, you know, my second set of fibers are going to be used for the protection. The first set of fibers I can use, you know, all 48 or 192 or whatever STS1s in. In 2-fiber, you end up having to allocate the restoration path against the bandwidth of the ring. So if you have an OC48 ring and you are using 2-fiber BLSR, you can actually end up with, and you want to do full protection of all the services going across it, you will never get more than 24 STS1s of traffic through that ring, because you have to use the other 24 STSs for backup, for protection. Now, I mentioned earlier that the mechanisms use an out-of-band mechanism for communicating that a switchover should occur. This is both for BLSR and for certain types of APS switching, certain types of linear switching. And for that, the signaling is done within the SONET overhead in the K0 and K1 bytes. Now, as I mentioned, SONET has a number of service level items which can actually cause a protection switch. It isn't just a simple, gee, light's gone, that causes a switch. It can be loss of signal, loss of frame. Loss of frame would mean that there's no underlying framing going on. Yeah, I'm getting a signal, a carrier from the other end, but I don't have any frame, or the framing's incorrect. It could be a threshold crossing. Thresholding means number of events within a specific time period. So I could have, for instance, more than 100-bit error events within a 15-minute sampling window. Coding violations. How many of you are familiar with how T1 coding is done? Okay. I'm talking about the actual underlying how the services get put onto, or how the bits are put onto the wire. In T1, it's using a mechanism which basically makes certain that you do not signaling of a 1 requires I'm a data guy. Requires a change. Requires a change. Requires an inversion of the polarity of the signal wire, whereas a 0 doesn't require the inversion. Well, what happens if you have both wires on a particular side of a T1 that are both high at the same time? There is no polarity difference between them. That's actually considered a coding violation. And B8ZS takes advantage of that in order to deal with the zeros density problem that exists with T1 lines. But in SONET, if you end up with a coding violation, that can actually cause a line protection switch. SONET also has something called a pointer within the overhead bytes This is used to deal with the fact that SONET rings operate synchronously, but the services that they're carrying may not operate from the same clock source that SONET is operating from. So the pointer field within the overhead allows you to do something called justifications or frame justifications, so you can deal with the fact that you may have time sources that aren't fully in line with the SONET time source. If you end up with too many pointer justifications happening within a particular sampling interval, that can also cause a protection switch. Last, there's the alarm indication signal. This is not talking about necessarily the T1 AIS or T3 AIS, but rather a SONET level AIS that's occurring because of the fact that there may have been a span break 2 or 3 nodes away. The AIS is a dummy field or a dummy value that comes in to the line so that you can determine that a failure has occurred and that it's okay. Now, all these mechanisms can be applied to MPLS. Why would I want to do that? Well, you can get fast restoration of your MPLS services. You can also end up with service recovery being done on a service-by-service basis. And here we talk about the typical Olympic model where you have best effort, which may be biased to extra traffic links. Heck, they can deal with the fact that there's a need to reroute, right? Bronze could be put onto unprotected but avoid extra traffic. Silver could be put onto shared restoration, and gold could be put onto dedicated restoration. That way, the different services being put across the network can benefit from different protection mechanisms that may be available. How would this actually be done? Well, same way that I mentioned earlier, you would have a route determination done for your primary path across your network. This would be an MPLS TE route determination. You would then signal the creation of the working path across your network. You can then set up a constraint list based on all the elements and the links that are being used to meet that working path, and then do a route selection for a working path that avoids all of the items in that particular element and link list. Once you determine that, you can then signal across that path for your protect path. Now, it should be noted that this can be a shared protection as well as dedicated protection. For example, you could have this protect span used not only to deal with traffic going from A to D, but also to deal with traffic going from A to B. Remember, this span here, if it's non-dedicated, can be used to carry any service, including the A to B service. So if you had a failure of A to B but not of A to D, you would potentially use this path in order to restore it. Yes?
Are you saying that your LSRs are talking to your underlying optical or silent equipment?
This could happen actually at any layer within the protection hierarchy. It doesn't have to be something specific to an IP LSP. It could be an optical LSP. You can use it anywhere. MPLS is being turned into a generic mechanism for any type of transport. It could actually be used at the IP layer, where you build two separate LSPs to handle the same forwarding adjacency, or it could be used at the optical layer, where you build two separate light paths and have the optical equipment do the sensing and switch over. Okay. Now, in order to pull this off, in order to do protection, you do have to make some extensions. For example, you have to have the way to identify what the diversity is of all the different network elements and links that go between source and destination. So a new constraint is added to the MPLS TE environment called Shared Resource Link Group. Now, the SRLG can represent anything dealing with diversity. For example, duct banks, they could have SRLG associated with them. How many of you understand what I mean when I say duct banks? Okay, that's the actual conduit that the fiber's going through. Okay, typically when a carrier, an actual fiber laying carrier puts down the fiber, they don't put it in one conduit. They instead put in a duct bank of say 16 conduits, a 4x4 bank, and then we'll put the fibers through that. Another SRLG could be the point-to-point system that exists between two SONET repeaters. Another SRLG could be the central office that the traffic's going through. So you basically can have different SRLGs applied to any layer of the resource hierarchy. But you also have to have another set of extensions for CRLDP or for RSVP-TE, and this is to deal with the notification that there's been a failure. How do I let all the things upstream of me, if I'm doing merging, know that there's been a failure on this one link downstream from this tree of nodes, or a tree of LSPs. As well as you also need to be able to deal with the fact that a protect path may not be put into service immediately, that it may be shared, that you may let the bandwidth which is associated with it be allocated to 2 or 3 different protection paths. So there are changes that are necessary in the signaling mechanisms used in the MPLS environment. But the neat thing about this is that when you think about what's happening with generalized MPLS and the fact that this really does create a protection mechanism for mesh networks, you can apply this to anything. You could apply this to SONET. You could apply this to optical. You could apply this to T1s even. You do not have to say this is good only for IP. It can be for pretty much anything that operates in a mesh environment. In fact, when you think about what generalized MPLS is doing, there are some other things that you can do. Rapid provisioning of lower layer connections. For example, let's say I have a network and the initial configuration of the nodes is in a hub-spoke sort of topology. I identify a high traffic load between 2 devices within that topology. I can now directly signal into the optical layer for a cut-through path to be established, thereby avoiding the hub node. So generalized MPLS has a number of things that it can bring to the network. In summary, new services like voice over IP and virtual leased lines require mechanisms capable of recovering working traffic in as fast a time as possible. Optical layer protection tools allow you to do this with the least amount of overhead. You can have one optical layer protection switch potentially bringing thousands of services back up at one time. You still need to do service layer protection, but you don't want to rely specifically on service layer protection because you can end up with signaling storms as a result. I know of 3 particular carrier network crashes where significant numbers of nodes and significant services are brought out of service for a period of time because of the fact that they ended up with a signaling storm resulting from an initial protection switch that wasn't handled at a lower layer. There are ATM switches in one of the particular crashes where they lost 80 of 120 ATM switches. That's a lot of traffic that's suddenly brought down. But they're a wholesale carrier, so they didn't have to report it. That's humor. Okay. MPLS TE with extensions can provide protection support for IP networks, but it can actually be extended to any type of mesh topology transport network that exists, and that it can then be used to integrate the control planes, allowing IP services to potentially control lower layer transport technologies. Any questions? Yes?
It seems like protection depends a lot on detection. And you talked about SONET detection using ARMS. What about the optical?
Repeat the question.
The question is that protection is dependent on being able to identify a condition where you need to do a protection switchover. And I've mentioned a number of items that are used as criteria for SONET protection switching, what sort of protection switches would you potentially do, or what sort of criteria would you potentially use at the optical layer to determine whether or not a protection switch is necessary? I mentioned a couple. One of them is loss of light. That's the obvious one. No carrier, not good. Another one is a loss of power. Now, what do I mean by loss of power? You could still have a carrier coming in, but due to, say, a microbend that's occurring in the fiber plant, you end up with some energy which is lost out of the fiber bundle because it ends up actually going outside of the fiber itself. Or you could end up with increased dispersion because of a microbend. Are you familiar with what microbends are? Okay. Let's say we have a near miss from a backhoe. They end up denting the conduit, but not actually breaking through it. Well, in the process of denting it, they may have actually caused the cables to be constricted within the conduit itself. And so you can end up with a pressure point existing on a fiber. That is called a microbend, where you have a bend occurring. It's not, somebody snapping it, but it's enough to cause energy to leak out of it or for the dispersion characteristics to change. So that power level is another thing that you can switch on. Optical AIS. Now you're probably scratching your head going, optical AIS, why would you want to switch on that? AIS, as you may remember, is the signal that gets passed along the line from a piece of equipment that knows that a next hop up the line had a failure, or somewhere up the line there was a failure. So if I've got a string of equipment, there's a span break between the first two devices, device 2 will insert an AIS signal into the payload path, and therefore all the downstream nodes will know that there's been a failure. Well, if you have global protection, you can actually then restore based on the fact that you received an AIS signal coming along the path to your protection path. So optical AIS is actually another thing you can use as criteria. Those are the ones that I come up with just thinking real fast. There's another issue that comes up with purely optical networks. When people are building optical switches, there are actually two different ways they can build them. One is with electrical to optical conversions in them, and implicit to these conversions, you end up with amplification of the signal. However, it's also possible to build the switch using all mirrors. And so as a result, there's no amplification of the signal. So you could end up with a particular path in use that, due to a protection switch somewhere else or bad engineering, doesn't have enough power in order to properly receive the signal at its destination. So that'd be another case of where power would be a good thing to switch on. Those are the ones I can come up with. There are certainly others. I've heard of one carrier which is thinking about changing the multiplexing mechanism, or excuse me, it's not a carrier, it's an equipment vendor, changing the multiplexing mechanism that they use to put multiple signals onto a fiber, so that instead of using wave division multiplexing, which is really just a form of frequency division multiplexing, that they actually use a spread spectrum mechanism. They actually do some sort of CDMA-ish thing in order to put multiple signals on the fiber. That kind of is interesting, but there are probably other modes as a result that would cause for a protection switch in that environment. Yes.
I guess auto lock can be protected another downstream.
Yes.
That assumes the reverse direction path of the optical layer.
It assumes that there's at least a control path that allows you to signal to the upstream node that there should be a change, or that you're doing some sort of path-based switching, and therefore it doesn't necessarily require the upstream node to know that there's a need for a change.
So there's standards that talks about...
There's a lot of work going on in the standards communities, but there is no proper standard for optical switching at this time, for optical protection. Other questions? Yes?
We already have standards in the optical domain.
Come to the next IETF meeting and see what sort of arm wrestling goes on. Actually, there are 3 different bodies that I know of that are working on standards for optical protection switching right now. outside of the obvious ones of ring-based protection, that sort of thing. Mesh-based protection is really spending a lot of their energies. And they all have different models for how you would go about doing the protection. And I think that's going to create the biggest incompatibility between vendors. The great thing about standards is that there are so many to choose from. So IETF has its idea. ITU is actually working on a mechanism now, and so are a couple of other ad hoc groups, ODSI, OIF, so forth. Yes?
To what extent is your knowledge, what's the difference between DWDM and SONET? Or is there a difference?
Oh, there's a difference. There's a difference. In a DWDM environment, all you're doing is taking multiple services and putting them onto the same fiber. There's no switching going on in a pure DWDM system. Where you actually get into switching would be an optical switch or in a SONET switch, which you put at the end of your DWDM system. So DWDM doesn't have any switching capability. It's the optical switch or the SONET switch which adds that capability. How do these protection mechanisms work with them? Really, it's the same. The thing is, people are more interested in mesh networks today than they are with ring networks. So the optical environment really hasn't created a lot of ring implementations. There are a number of proprietary mesh implementations, from Sienna, from Sycamore, from Monterey, now Cisco, so forth. Other questions?
So in many instances, what you're saying is it depends on what's happening.
Repeat it for the people.
I'm sorry, could you repeat the question? I couldn't even hear.
In many instances, you're saying it depends on what type of equipment you're using at the SONET layer rather than the actual routing layer, the Juniper layer.
Yes, the question was, are you dependent on what's happening at the routing layer or at the actual transport layer to what sort of switching you do, whether it's SONET or optical? And yes, there is no dependency directly. The bigger issue you're going to run into is when IP devices start to signal for optical services. I mentioned this cut-through example. Then you're going to start getting into which model did they go with? Did they go with what's being called the pure model that IETF is working on? Did they go with what's called the domain hierarchy model, which is what ITU's pushing? There are even some people in ODSI that are pushing for that. The result is that you can end up with incompatibility between the two different layers. Yes?
But on the other hand, when you are very dependent also on the router in the MPLS arena, and how it detects if the optical layer or the SONET layer signals the failure, but the router isn't looking at that, then you've got to wait for the interface time.
Right.
Router vendors are doing it different.
Yeah, the follow-up comment was that the mechanism used by the routers to determine failure may be different from different vendors. Some are actually paying attention to what's happening at the optical layer. Some instead will have interface timers that have to expire before detection is made. Other questions? Yes?
Are you familiar with the Cisco APS implementation?
No, I'm not. The question is, am I familiar with Cisco's APS? And the answer is nope, sorry. Haven't actually worked with theirs. Other questions? Yes?
You had a comment early in your presentation about the need for coordination between protection domains.
Yes.
Could you talk a little bit more about that?
Yes. I do have a flip chart. Do I have any markers? Yes, I do. Okay. Excuse me, I have to walk away from the mic for this one. Or maybe I might be able to move it over here.
Bring it over.
Can you all see the flip chart? I'm sorry, for those of you that can see you see the flip chart? The question is, early on in the presentation I made a comment about the need for coordination between protection domains, and could I elaborate on that? And I'm going to draw some things on the board here. I'll try and stay close to the mic as I'm commenting. You could have a network with multiple protection domains existing between source and destination. So I've drawn a simple network up here, and I'm now going to divide it into 3 protection domains. What you see here are 2 ring networks on either side, and then in the middle you see what I'll call a mesh network. And it's a very simple mesh network with only 2 nodes in it, but it's a mesh network because of the fact that it's got other protection domains to the sides of it as opposed to direct user interfaces. The issue you run into has to deal with how does a service map onto these protection domains. You could have, for example, if you're using global repair, a path that goes from source to destination which traverses all the northern elements, and another path which traverses the southern elements. I have only one color marker. Sorry, there was a backhoe on that last link. So you see here now the 2 paths between the left and right side. Now the problem that you run into is none of these protection domains are responsible for the end-to-end protection or for protection within their domain. They have to harmonize with each other on how the end-to-end protection is going to be done. Specifically, if you look here, I've got 2 egresses to this protection domain for 1 service entrance, or for 1 service that's being carried. Likewise, over here, I have 2 services coming in for 1 service going out. How do I let the traffic go?
Your requirements over left,
the question had to deal with the coordination that may be necessary between the IP layer engineers and the SONET or optical layer engineers, and the fact that requirements should be provided by the IP engineers to the optical or SONET layer engineers in order to have them configure their protection mechanisms appropriately so that then IP can properly react. And this really has to deal more with organizational structure, the fact that you have 2 different groups dealing with the 2 different technologies, and then you have an interface point between the groups. Yeah, you certainly can end up with an issue where one group thinks that SONET is the be-all and end-all of where you should do protection, and we're going to do 50 millisecond protection regardless of whatever you want at the upper layer. Plus they may also do optical protection. They see SONET as their service layer, they see optical as their dirt layer, and now you start getting into the multiple stacks of, or the stacking of multiple protection layers. You need to look at it from a more holistic perspective. You need to say that the service that's actually being sold to the customer is IP, and then have your underlying service providers react appropriately. Now, how do you deal with that in an environment where you may have one service provider buying services from another service provider? Unfortunately, you do end up with inefficiencies there. Unless you have a very good partnership relationship with your underlying carrier, you could be relegated to what they have as public product. Whenever you start changing protection mechanisms in use, you're asking usually for an individual case-based price product. Yes?
You touched on an issue just then that I think several colleagues I know of are having a problem with, and that is understanding when one buys optical services, how to specify 4 fiber versus 2 fiber services. That is, what am I getting? Am I getting linear APS, or am I getting UPSR, or am I getting BLSR? What is the, inside that vendor's cloud, what kind of protection am I actually being provided with? Trying to find that out has been very, very mysterious and very difficult for us. It doesn't seem to me like we're alone in that particular mystery.
Yes. Yeah, the comment had to deal with the fact that in an environment where you have service providers buying services from other service providers, that sometimes there's this cloud of secrecy around how the underlying carrier has built their network. And so you end up with two issues. One is, what exactly are they implementing with? And the other is, how do you tell them that you want something different? And it really comes down to what is the business relationship, unfortunately.
The business relationship seems to be independent of the, well, maybe it's more dependent than I thought, but it seems to be an independent issue to the ignorance of the salespeople who are involved in the transaction. And the salespeople who are involved in the transaction are often people who say, well, I'm selling you 4 fibers. How are they configured? But they're 4 fibers. And
having been in an environment where I was working for a service provider that was buying services from an underlying carrier, I can understand the ignorance of salespeople issue. We usually short-circuited those discussions right to a technical engineer that was deep in the bowels of the network. Fortunately, I was doing this at a RBOC as we were getting into long distance. That's a long story. We'll talk about that separately. But as a result of it, we had the weight of our company behind us, and typically got good services from the wholesale carrier. That's the reason why I talked about the actual business relationship, is that the fact that you specified in your contract that you have a short circuit route into technical engineering, that really matters when dealing with those issues. Yes, you have to set up those peer relationships pretty early on. Yes.
I guess we're kind of talking about, from the end customer's perspective, what's their confidence level that the resource affinity or non-affinity diversity kind of requirements that they have are going to be met?
The comment had to deal with the confidence interval that basically exists with whether or not a customer's requirements for resource affinity are going to be met by a service provider. It should be noted that the comments that I made about SRLG and that sort of thing work great if you're running with peer model, where you have that information becoming available to the IP devices that are connected into your optical or SONET domain. But if you're running in the domain model, where you have, if you will, a uni interface, where you have all that information as to how the underlying facilities are set up. What does the duct bank network look like? What does the actual fiber routes look like? So forth. You're not going to be able to necessarily guarantee diversity. I know of. I mentioned earlier the company that did derivatives trading. They actually changed carriers because of the fact that one of their older carrier had said, yes, everything in the network is diverse. Well, since they do a lot of international work, they have connections going from the U.S. to the Far East, as well as also into Europe. And when they thought they were buying diversity, they thought that meant that to get to the Far East, they could go through Europe for the diverse path from the primary path. And it turned out that the diverse path was going through the exact same international POP in California, so they had no diversity. One misanchored tanker took their service out to the Far East. The way that you can start to validate whether or not the services that you purchased are diverse is through basically a session where you sit down with your carrier and say, produce all of the design layout records or DLRs for the services that I purchased, and show me that they really are diverse. Once again, this gets back into the business relationship. Not many typically, someone who just approaches an IXC and says, I want to buy services, won't get the DLR visibility. That's something that you typically have to negotiate to get. But once you have the DLR information, you can do an audit. The problem is that with the current way that IXCs operate, without automated systems to do diversity routing, typically what they have is basically just a big database which shows all the circuits, all the design layout records, and then it requires a human being to determine whether or not some activity they're doing in the network is going to cause diversity that's been ordered to be removed. So the result, anytime they do some sort of a regrooming exercise or rolling exercise, you can easily end up with with diversity lost. I know we're looking forward to being able to provide automated schemes to do diverse routing. Yes?
I talked to the NCI folks at one time, and they told me that it took them over 3 hours to calculate what effect that fiber change would actually have on their network. So they didn't check on every fiber change because they were making them more than there were hours in the day. If each one would take them 3 hours.
Yeah, I can believe it. I can believe it. It requires a lot of time. And a lot of the processes to do the diversity checking are actually manual processes. Yep. The comment was that, excuse me, if MCI had mentioned that in order for them to do a diversity check on every activity they have in the network, it potentially would take 3 hours for each check, and that because of the fact they had multiple activities happening in a day, they could easily exhaust all the hours in the day. Yeah, that's definitely an issue. That's one of the reasons why you find some carriers, excuse me, setting up their inventory groups based on how they've got their protection domains architected. You know, what is the geography of a particular group of protection domains, so that they can try and reduce some of those issues for how changes are going to affect services going through that domain. Because the protection domain makes a nice demarcation point for how groups interact with each other. Other questions? Yes?
First of all, so these diversity checks are done on fiber paths or light paths or matrix paths?
Question had to deal with what is the level that a diversity check is done upon. Really, the diversity check has to be done at every layer of network that exists between the service that's being sold and dirt. Now, even duct becomes important. I know somebody I worked with at the Sarbach that had a major customer that said, okay, I want to make certain that the services you've sold us are diverse. And so what they did is they hopped in a truck and they drove the routes. Well, this particular customer along the route said, wait a second, we've been through this intersection before. So they had diversity from the fiber perspective, but in reality, you know, there was a point that existed where both routes crossed each other. Okay, so that's where you start getting into duct diversity issues. You have to do it at every layer. And unfortunately, DLRs don't really show duct layer diversity issues. No, they don't. You know, DLR is typically written based on inventory tags that exist in a database. And so actual physical route isn't something that's really, you know, talked about. It's you know, you got this particular span of fiber going between this CO and this splice point or whatever. So you don't know if you end up with a fiber crossing issue. Yes?
Just another thing to emphasize in the DLR, what you said is very important. It's based on what they track in inventory. They don't track everything in their inventory. The DLR won't show you everything that's possible, just what they're tracking. And the problem usually is stuff they're not tracking what's going by.
Right, right. Yeah, the comment was that not everything's tracked in the inventory database. Since the DLR is only showing you what's in inventory, you cannot rely solely on DLR audit. You have to get some other mechanism. In our particular network, which we were building out, we had a place like that. And fortunately, we never had fiber cuts in that place. But we knew that there was an exposure that existed because of how our underlying carrier's network was built. And that's an important thing to think about when you're actually building out your own fiber networks. You know, where's a good place to put a POP or a place where you do traffic exchange? It probably would be good for you to have those demarcations occur where you're doing fiber crossings, because of the fact that you can usually switch around then. Other questions? Have I used up all my time yet? How much time do I have left? 15 minutes? Okay. 15 minutes worth of questions. Anyone? Yes.
Do you have any idea how far out optical switches that implement MPLS are?
How far out are optical switches that implement MPLS? There are actually a lot of companies working on them. I would submit we're not talking 5 years. We're talking in the couple years maximum range. Okay. Other questions?